This video introduces the concept of transactions in interactions with database systems. Transactions are a very important concept. The concept of transactions is actually motivated by two completely independent concerns. One has to do with concurrent access to the database by multiple clients, and the other has to do with having a system that's resilient to system failures. So we're going to talk about each of these in detail in turn. Let's take a look at the software structure of how database systems are used. We have the data itself, usually stored on disk, and then we have the database management system, or DBMS, that controls interactions with the data. Often there's additional software above the DBMS, maybe an application server or web server, and then interacting with that might be human users or additional software. And the types of operations that these users or the software will be issuing to the database are the things we've looked at, such as select commands in SQL or update commands, creating tables, creating and dropping indexes, maybe a help command, a delete command. So each of the clients or the software applications will be issuing these types of commands to the database, and most importantly, they will be issuing them concurrently. And we might have, a database with one user, 10, hundreds, or even thousands of users at the same time. Let's look at the kind of difficulties we can get into when multiple clients are interacting with a database at the same time. We'll be focusing mostly on SQL statements, modifications, and some queries that are being issued by clients, and we'll look at some different levels where inconsistency can occur. We're going to focus our first example just on a single attribute and how we can have problems when multiple clients are working on the same attribute. So let's say we have two clients. One is issuing a statement that's increasing Stanford's enrollment by 1,000. The second client, around the same time, is issuing a statement that's increasing Stanford's enrollment by 1,500. So we have in the database our college table here, and somewhere in this college table we actually have Stanford's enrollment. Now the way database systems work is when we are modifying a value in the database, effectively the system first gets the value, then it modifies the value, and then it puts the modified value back in the database. So here's the value that we're working on. So client S1 will fetch the value, add 1,000 to it, and put it back. Client S2 will do something similar, but adding 1,500 instead. Let's suppose Stanford starts out with an enrollment of 15,000, and these two statements are executed concurrently. What are the final values that we might have? Well, if one of them runs before the other completely, then we'll add 2,500 and we'll get 17,500. On the other hand, if they really can interleave their get, modifies, and puts, then it is possible that we'll instead only add 1,000 because the 1,500 gets lost, or we could only add 1,500. So there are three possible final values if there's interleaving of the operations that modify the value. Of course, we're going to see that there are mechanisms in the database to avoid this, but I want to motivate the reason that we have to have those mechanisms. Now let's look at an example where the inconsistency actually occurs at the tuple level. Again, we're going to have two clients that are both issuing statements to the database that will have some conflicting behavior. In this case, they're both modifying the apply record for the student with ID 123. The first client is trying to change that apply record to have a major that's CS, while the second is modifying a different attribute of the same record, saying that the decision should be yes. Now let's take a look again. So we'll have our table here, and now in this case we're looking at an entire tuple. Let's say that this is student 123, and so we have, say, the major in here and the decision in here. Now I mentioned already that the databases tend to use a sort of get, modify, put, and we talked about that at the attribute level previously, but in fact the reality is that it does occur at the tuple level. In fact, sometimes it occurs at the entire page or disk block level. So let's suppose that it occurs at least at the tuple level. So again, we can see the same problem then when we have the two clients. They each will be performing a get, modify, put. If they do it interleaved, then it's possible that we will see both changes. Then it's possible that we will see both changes. We'll correctly get the major reset and the decision reset, but it's also possible we'll only see one of the two changes, and it could be either one. So again, we need some mechanisms to ensure that we have consistent updates to the database that would give us what we expect. In this case, we would probably expect both changes to be persistent in the database. Now let's go one step further and look at table level inconsistency. Again, we have our two clients, and they're submitting statements to the database around the same time. One of them is modifying the apply table, and it's setting the decision for applications to yes for every student whose GPA is greater than 3.9. The other statement, occurring at about the same time, is modifying the student table. We've decided to increase the GPA of every student who comes from a large high school. So here we have the apply table, we have the student table, we have the first client, S1, working on the apply table, but the conditions in which apply tuples are updated depend on probing the student table. Meanwhile, we have client S2 that's modifying the student table. So what happens in the apply table can depend on whether it occurs before or after or during the modifications to the student table. So, students would certainly prefer if their GPA is increased before the apply records are automatically accepted based on the GPA. So again, a notion of consistency here would be that we understand that either all the GPAs are modified first and then the acceptances are made, or vice versa. And we'll again see mechanisms that will help us enforce that. As a final example, we'll consider clients that are interacting with multiple tables again, but in this case we also have multiple statements that are playing into the situation. Specifically, we'll see an example where we will want one statement to not occur concurrently even between the statements from another client. So let me just show the example. So here again we have two clients. I'll label them C1 and C2 now, since the first one has two statements. So what the first client is doing is moving records from the apply table to an archive table. Specifically, it looks in the apply table for records where the decision is no, and it inserts those into an archive, and then in a second statement, and this is really the only way to do it, it deletes those tuples from the apply relation. The second statement, the second client, just happens to want to count the number of tuples in the apply table and in the archive table. So again, we have our two tables that we're concerned with, the apply table and the archive table. And what the first client is doing is it's moving some tuples from apply to archive, and then in a second statement deleting those tuples from apply. Our second client, I'll put this one in red, is counting from the apply and then counting from the archive. Now, if we want the second client to see sort of a consistent state of the database where we don't have records that are duplicated between apply and archive, then we will really want that second client to go either completely before or completely after the first client. So after that long sequence of examples, I hope you get the feeling for what we're looking for in concurrency. We have multiple clients interacting with the database at the same time, and if they have true interleaving of the commands that they're executing on the database, often update commands, but some select commands as well, then we may get inconsistent or unexpected behavior. So what we'd like to have overall is the ability for clients to execute statements against the database and not have to worry about what other clients are doing at the same time. Specifically, a little more generally, we'd like clients to be able to execute a sequence of SQL statements so that the client can at least act like those statements are running in isolation. Now, there's one obvious solution to do this, right? Why don't we just execute them in isolation? The database system can take its client requests and just do them one at a time with no concurrency. On the other hand, we really do want to enable concurrency whenever we can. Database systems are geared towards providing the highest possible performance. We talked about that way in the introduction to the course. And they typically do operate in an environment where concurrency is possible. They may be working on a multiprocessor system. They may be using even a multi-threaded system. And database systems also, as they access the database, tend to do a whole bunch of I/O. So a system that provides asynchronous I/O can also run multiple things concurrently. It can do one thing while it's waiting for data to be fetched by another. So assuming the system supports concurrency, then we would like the database software to support it as well. As a very simple example, let's suppose we have 5 clients that are operating on the database, and each one of them is operating on a completely different part of the database. Then we certainly wouldn't want to force them to execute sequentially when they could execute in parallel without causing any inconsistency problems. Let's switch gears entirely now and talk about system failures. Again, we have our database system working with the data on disk, and let's suppose we just happen to be in the process of bulk loading our database, maybe bringing in a large amount of data from an external source, say a set of files, and right in the middle of that bulk load we have a system crash or a system failure. Could be a software failure, could be a hardware failure, it could be as simple as the power going out. So if the database is at that point half loaded, so let's say half of this data has made its way to disk and the other half hasn't, what happens when the system comes back up? That leaves us in a rather unpleasant, inconsistent state. Or maybe we're just executing some commands on an existing database. Remember our example earlier where we were moving tuples from an apply relation to an archive. So we have our relations here. We're in the process of moving some data, and then once it's moved, we're going to delete the data that we moved. And then all of a sudden, once again, we have a crash or a failure of some type right in the middle of that move. So what do we do now? When the system comes up, how do we know what was moved and what wasn't? As a last example, let's just suppose we're performing a whole bunch of updates on the database. And as a reminder, the way database systems perform updates is they bring some data from the disk into the memory, they modify it in memory, and then eventually they write it back to disk. So let's suppose in the middle of that process, again, we have a system crash. That would again leave the database in an inconsistent state. So our overall goal for dealing with system failures is that when we want to do something on the database that needs to be done in an all or nothing fashion, we'd like to tell the system that we want to guarantee all or nothing execution for that particular set of operations on the database, regardless of failures that might occur during the execution. So we've talked about problems with concurrency, we've talked about problems with system failures, and interestingly, the exact same mechanism can be used to deal with both of those issues, and that mechanism is, not surprisingly, transactions. So overall, a transaction is a sequence of one or more operations that are treated as a unit. Specifically, each transaction appears to run in isolation, and furthermore, if the system fails, each transaction is either executed in its entirety or not at all. In terms of the SQL standard, a transaction begins automatically when a SQL statement is issued by a client to the database. When the commit command is issued, that's a special keyword, the current transaction ends and a new one begins. The current transaction also ends when a session with the database terminates. And finally, there's a mode called auto commit, and in this mode, each SQL statement is executed as a transaction on its own. So for each client, we can actually think about a timeline, and the client will be executing along. It might say commit, and that will commit anything that happened prior to this point. Then it might do some operations, maybe a select, an update, a delete, and then it says commit again. And when it says commit at this point, that turns this amount of work into a single transaction that's treated as a unit. Maybe it'll update, maybe it'll create an index, and again, maybe commit at this point in time. And that right here will turn this into a transaction. And so we can see for each client, this is client 1, their execution on the database is seen as a sequence of transactions, each of which has the properties that we described. And then we may have a second client that's also operating on the database, and then it will also have its set of transactions. In the next video, we'll give more details and a more formal treatment on the properties that are guaranteed by transactions, both how they operate individually and how they interact when multiple clients are executing on the database at the same time or when the system fails.